So the tool is available on my GitHub, which is available through my courses. So if you go on my courses, well, I don't have it saved here. So I'm just going to go to it directly because I already have it saved here. And this link is available on my courses, and it'll be posted how-to videos and guides on how to use it. And there is in our Zoom chat if you want to download it. This app will graph the time complexity of our methods. So it's going to look like this. It's going to have a window with a graph, and it's going to show us how the input size determines the speed of our function, just as we talked about earlier. Now to install this app, we go here to the releases page, click on releases. I'll take the latest 1.2. You choose the right one for your operating system. So here I'm on Windows. So I'm going to take the Windows version, and I'll keep it, ignore that it's a virus. And it's going to be very easy to use. So you're going to go into your IDE. In IntelliJ, you go into Project Structure, which is this button right here. You go into Libraries, plus Java. Then you just drag your file in. So where did my file go? Let's find it. I will show in folder. Find my file. I guess it just went straight to my downloads. I can drag this into here. Drag this into here. And click OK. Then it's going to load the library. I'm going to press OK. If you guys went to ECSE 202, you'll remember this is how you installed ACM. And now I've got the library installed in my IntelliJ. So nothing really changed. My apps all run the same way as they used to. Like everything I run will work the exact same as it always did, except for the fact that now I have the ability to test time complexity. So yeah, all my apps open normally. Everything is as it was. But if I now go into my program and I want to see how fast something is, I can do that. So if I go into Engine here and I create a new, or if I create a main method, do we have a main method right now? No, we don't. So I have to be able to run it. I have to create a main method, public static void main string args. Right? And I want it in here, I'll just put visualizer dot launch. And that's it. So if I click run on that, now we're going to get a really fancy looking pop-up. Oh, what's wrong here? Oh, I also have to say visualizer.launch, and I have to put in the argument of engine.class. And now it should go. And there we go. So we have to pass it the class name that we set, and then we'll get this fancy window with all these graphs. Now these graphs might be hard to read at first, but what we actually give you here are examples of how fast things run. So we've got our built-in methods for Java, and we've got mathematical demos. So if I just show you guys mathematical demos, we can see how fast n squared, O of 1, and O of n, and O of n log n are. You can see in blue we have O of n, in orange we have O of n squared, and in green we have O of 1. And we can see how their graphs relate to each other. And we can also see that as we increase our steps per iteration, which is basically like taking the limit as n approaches infinity, we can see which ones stay big and which ones don't. If you remember in calculus, when you take a limit, you can just ignore everything but the highest power. This is the same idea. We can see here that n log n, O of n, and O of 1 all became insignificant lines at the bottom, which may as well be 0. And O of n squared has exploded up to be the only thing that matters, right? This is how we can determine time complexity. Remember in the slides how I said that we have big O, big omega, and big theta. And how big theta is how fast our method actually is, or more so, it's a binding of how fast our method actually is, right? If this is big O of, or if this is big O, and this is big omega, then big theta is what's in between my hands. So what we need to do is we need to find our big theta. How do we find our big theta? Well, what we do is, let's say we want to find the big theta of this Q get from middle. If we graph it by itself, doesn't tell us much. But now, if we graph it next to O of n squared, we can see that O of n squared is definitely higher. So at the worst, so what can we gather from this? So from the graph, so O of n squared is much bigger than our method. Right? What else can we gather from our graph? Well, nothing right now. So let's also compare it to something else. So it's definitely way, way better than O of n squared. Now if we compare it to O of 1, what can we say? Well, we can see that our method is definitely way worse than O of 1. O of 1 is just a line at the bottom, and our method is just running away from it. So we can say that O of 1 is way better than our method. Okay, so we're narrowing it down. So right now, our big O of n squared is way worse than our method. That's what I meant to say. O of n squared is way worse than our method. So these should be facing different directions. O of n squared is way worse than our method. O of 1 is way better than our method. So maybe our method could be compared with O of n log n. Well, we can see that n log n is still worse than our method. It's O of n is O of n log n. N log n is worse than our method. So that could be a good maximum, right? That is worse. It's still quite a lot worse. And how about O of n? How does it compare to O of n? Well, it's pretty close to O of n, right? Like we can see they're growing at a similar rate. They're very similar, right? So we could say that our method is probably O of n, right? So O of n approx equals our method. Right? Our method, it never goes above O of n, so it's bounded by O of n, but we could see it's increasing at roughly the same rate. Our peaks are kind of as big as O of n. Of course, we sometimes drop, we sometimes go down, because again, as we showed in our slides, our actual speed will kind of be oscillating between our big O and our big omega. So we can say that our big O is probably big O of n. And if we want to find a big omega for this, we could also do a similar thing, but we're basically never asked for big omega. We don't care really in Comp 250. But if you want a big omega, you could maybe say log n, not sure. We never tested it. We don't really care. We only care what is our big O, and in this case, we can say that it's big O of n. So we found the time complexity of this method, right? Does this make sense to everybody, how we did that using this graph? All right, but what we might see as missing here is actually our own methods. Because right here, none of the methods we wrote are showing up in this list. So to put these into our own list, we actually have to do something called an annotation. If you remember previously, when you were writing your code last assignment, if you were using IntelliJ, you might have sometimes seen annotations, which look like at override, for example, is an annotation. And again, they're denoted with the at. So what we have to do is we have to write what's called a benchmark method. The benchmark method, which we will annotate with at benchmark, will have a name. So let's call our name equals our bubble sort. And here, we're just going to write our normal method. I'm going to import this as well. It needs to be imported. So boom, boom. Our bubble sort. Now to test the speed of our bubble sort, I will now create a public long. Long is going to be the data type we use to return how slow it was. Test bubble sort, and we can name it whatever we want. It doesn't matter what we call our method. I just call it test bubble sort for whatever reason. And it's going to take a long input, and that's going to be the size of our input. So input is the n. Oh, this should be a comment. Input is the n we are talking about for big O of whatever, right? So big O of n, this is the n we're talking about. And how do we do this? Well, first we have to make sure that the input corresponds to the size of our data set. Here, our data set is going to be an array of layers, right? Because we sort this array of layers. So let's generate an array of layers of the size n. We'll first create a randomizer. Random rand is equal to new random. And then we're going to fill up. Sorry, go ahead.
Could you just say again, what was the purpose of putting the at benchmark label above the method you're typing?
The at benchmark label will tell our application, the one that we just showed with the graphs, that this method is one that we should graph. So this basically says that this method can be graphed.
Okay.
And the requirements for a method to be graphed are that it can take as input a long, and it can return a long. Anything that takes a long as an input and returns an input or returns a long is going to be graphable. But of course, to get valid results, we need to follow some rules. So we need to fill our data set up to the length input. So for long I is equal to 0, I is less than input. Well, actually, I guess first we need to create our array. So we'll say layer array test subject is equal to new layer array, and it's going to be of size input. But of course, arrays can be of a maximum size that's an int, so that's fine. It's not like we're going to run a test big enough to be a long. So I'm going to cast this to int, right? But that doesn't work either, so I'll have to do .int value. Again, the only reason I do this is that the size of an array can be maximum of an int. The reason I have it as long in the library is just because sometimes we need to test things that are really massive, so we have the possibility of using a long as the input, but really doing the int value is okay. So here we've got our test subject, which makes an array of the size input. Now we can say for int I equals 0, I is less than test subject dot length I plus plus. We're just going to fill it up. So we're going to say that test subject at I is equal to new layer, and then we just care about our depth. So we're going to say null content and rand.nextInt for our depth. So what does this do? The above code fills up the array with layers of random depth, and then we need to sort them. So we already have the array. Now we have to call the sort. So we can just say sort test subject. But how do we figure out how fast it was? Well, the way we do this is we actually basically use a stopwatch. We determine at what time did we start and what time is it when we finished. So we can say that long start time is equal to system.nanotime, which takes the current time in nanoseconds. We can say long end time is equal to system.nanotime as well. And now this method just takes the time from your computer in nanoseconds. And then we can return start time minus end time to get how long the method took, right? Because this is the time when we started. And this is the time when we finished. And then that returns the difference. So now we have this test. We don't need to call it anywhere. We can just click run. And then we'll be able to test the speed of our bubble sorting method. Now, there might be an issue with our bubble sorting method where it doesn't sort arrays of length 0 because it looks like it's not graphing here. So let's see. Will our bubble sort... let's just say that if layers... I'm just adding this because it looks like it's not graphing. So if layers.length is equal to 0, we will just return. Maybe that's why it didn't want to graph. Let's see. Okay, so for some weird reason, it doesn't want to graph my bubble sort, but that's okay. This happened last time as well. This should work when you do this format for any arbitrary method. We can just do a different example here where we return n squared. So we can just return, comment that, and if we return math.pow input 2, what's wrong with this? Double math.pow with long. Why is it not like that? Oh, it doesn't like that it's turning into a long, so we could say long.value of. Okay, finally. Now this should graph just fine. It doesn't like that. It doesn't like that. So bada boom, bada boom, bada boom, bada boom. And now, finally, we should be able to see it graph our own method. I think it's something with our bubble sort it didn't like. Maybe the fact that it used layers. Or no, it just doesn't like something about my method here. But regardless, yeah, it doesn't like something about it. Not going to figure out what that is right now. I'm going to do a pre-recorded segment on how to make these tests of your own anyways. So again, misbehaving right now, some technical difficulties. But generally, this is how you do it. Like this is how these work. And then this, well, yeah, I forgot. It's static. Sorry. How silly of me. Not technical difficulties. I forgot a very important step. This method has to be static because you don't have to instantiate the object to run it. Now, if I run this, we should get a graph. I should really throw a compile time error for that. Okay, so here's our bubble sort, and we can see it run. And if it doesn't tell us much, but if we compare it to our theoretical n squared, we can see that it pretty much exactly lines up with n squared. Our bubble sort basically, you can see how it follows n squared pretty closely. pretty much shows that our bubble sort is n squared. Now sometimes it goes above, sometimes below, because this n squared method is literally taking the number input and it's squaring it. And now it looks like our bubble sort is somewhat being strange after size 60. That's probably because our bubble sort's not very stable above a certain size. So that might not be super accurate. But we can see that it's not being crushed by, or yeah, it's not completely being crushed by O of n squared. It still has some significant value, even when we square the input. And because of that, we know that these two graphs only really differ by a constant. So we can say that our bubble sort is O of n squared. We can see that our bubble sort is definitely much slower than O of 1 and O of log n. In fact, if I increase my steps per iteration, we can see our bubble sort really is much slower than both O of 1 and O of log n. We can see how it's just skyrocketing. So that's the time complexity of our own bubble sorting method. And yeah.